you guys have made fuel, or like where? I'm just trying to get an idea of where people's level of understanding is. So it's like half the people, which is pretty good. And the rest of you, have you researched that whole process at all? Do you need to start from the beginning a little bit? Who hasn't? Who feels like they're really starting at the ground floor? Okay, cool. So I'm going to do what I call cartoon chemistry, which is basically do a little bit of a diagram of what the chemicals that we're working with look like and how they interact. And a few of you have been in my classes and you've seen this endlessly, but so I'm just going to write that on the board and then go explain and write a couple of reactions on the board, and then I will go back and explain it. Unless you want to do this for me, because it's going to take a couple minutes and I can't talk it right.
Okay.
Do you want to do a triglyceride, diglyceride, monoglyceride, and then three biodiesels? Just in the same way. And then I'm going to do the products. So whatever formulas. So. So when we make biodiesel, we keep talking about making biodiesel out of oil. Just for the, actually nobody really said they're a complete beginner, so maybe I don't have to go that far. But essentially what's happening is we're reacting vegetable oil with methanol. We make two products. We make biodiesel and glycerin. And the process is a way of making one kind of an ester into another. Esters are compounds made out of an acid and an alcohol, and in the case of vegetable oil, it's an ester because it's actually got a portion that kind of looks a lot like a glycerol molecule. Glycerol is a heavy alcohol, and then it has a portion that looks like fatty acids that are attached chemically. And so a lot of what we're doing has to do with how much those two pieces come apart. And so unfortunately, oil doesn't just instantly turn into biodiesel. It makes a couple of intermediate compounds, and that's what she's drawing out here in cartoon chemistry. So we have oil molecules and a couple of intermediate things, and then a little diagram, little circles that stand for biodiesel. You want to put a methanol in them, or
yeah. Do I want to add like?
No, those are actually good. But okay, never mind. They're far enough advanced, I think, but it doesn't matter. I just want to kind of talk about the structure of what those intermediate compounds are, which helps us when we look at trying to test for them as homebrewers. Also, I'll talk about why we don't want them present, and then also other kinds of quality control factors that you want to watch out for as far as biodiesel production. So oil's an ester. It's got what looks like three fatty acid chains, like fatty acid molecules, that are bonded chemically to a glycerol backbone. When we start in the presence of lye or the presence of potassium hydroxide or sodium hydroxide, essentially we start breaking this bond down and forming fatty acids. And when we make biodiesel, we're hoping that those fatty acids then go on to becoming part of a biodiesel molecule. Biodiesel actually looks like a fatty acid chain and methanol stuck together. And then another thing to point out is that the fatty acids are what gives oils their properties. So fats being solid is a property of the type of fatty acids that fat is made up of. Whereas soybean oil being liquid means that property is caused by the fact that that's the fatty acid portion of this oil molecule that makes the difference between oil and lard. They both will go through the biodiesel process fine and so forth, but the results will look really different. Things that you make from oils versus fats will look really different based on the fatty acid profile of that oil. And sometimes that affects us in terms of our production. There's some obstacles in terms of production when you make stuff that solidifies. Sometimes that's linked to there being fats. That just causes handling problems. And then there's a few other a few other properties that are directly influenced by what kind of fatty acid the oil had in its composition, oils had in their composition. And glycerin is glycerin no matter what kind of oil it comes from. Like if your whole goal is to make glycerin, it really doesn't matter if you start with waste vegetable oil or new oil or fat. Glycerin is all the same. Fatty acids are what really varies a lot. And sometimes this is where I think some of the quality control problems that people have seem to sometimes be linked to, whether quality control problems are really visible as problems or if they're just poor quality biodiesel that doesn't cause problems. That seems to be kind of tied to what the stuff was, what kind of fatty acids were involved. Anyway, in the process of going from oil to biodiesel, each oil molecule in your sample goes through kind of several steps on the way. And this has all been much better described by John Bush, but in the simple version, first thing that happens is you basically break off a fatty acid chain out of this E-looking, triglyceride oil molecule. Break it off, you are left with, and that hopefully goes on to form a biodiesel molecule. Hopefully that reacts with methanol, goes off, makes a biodiesel molecule. Next thing you're left with out of that starting material, you've got what's called a diglyceride, which is two fatty acid chains attached to glycerol. And then you're hoping that you have enough methanol around it, and enough lye around it, and it will then break off the next bond and then leave you with a monoglyceride and two biodiesels. And then hopefully if conditions are still right, you'll break off your third fatty acid chain off of that original oil molecule and you'll make your third biodiesel molecule. And then at that point, what's left of the glycerol backbone has really different properties than it did when it was part of what Bob called bound glycerol this morning, meaning glycerin that's part of oil or diglycerides or monoglycerides. There may be a lot of confusion for some people about what we mean by glycerol in vegetable oil, because when we make biodiesel, people are very, very concerned about free glycerin, the glycerin that settles to the bottom of your sample when you have reacted a batch of oil to make biodiesel. You'll get liquid glycerin that'll settle off. But then when we talk about quality testing from a commercial perspective, or from a lab perspective, we always talk about glycerol as in this bound form, where it's a really different compound than the stuff that's at the bottom of your Dr. Pepper batch in the lab back there, the sample that people made in the lab. So bound glycerol has, how many people went to Bob's presentation this morning? So they kept talking about like a very small percentage of bound glycerol, and what they were really calculating was just how many actual glycerin backbones are floating around in a whole bunch of diglycerides and monoglycerides. So essentially, diglycerides and monoglycerides are a compound that has properties that are sort of halfway between glycerin and oil. They're oily. They'll float in your biodiesel because they are oil soluble. They're not water soluble like free glycerin is. And so there's no way to filter them out really, and they're easy. You can't really wash them out when you water wash your biodiesel as part of your processing. So it's kind of it's sort of a hard contaminant to remove. And usually the goal, in terms of getting what we call complete conversion, is to try to minimize how much monoglyceride and diglyceride is left over when you are, or triglyceride for that matter, which is just straight up oil. You want to minimize how much of that is contaminating your biodiesel. And you also, there's a number of other contaminants. The mono and diglycerides are kind of hard to test for, so people get very concerned about them, and they're hard to kind of remove once they're formed without doing another step of the same, conducting your biodiesel reaction again. So people get very concerned about it. But there's a few other contaminants that we worry about. Free glycerin. If we make, even no matter how much, how fully you convert your oil, you also have the additional step of making sure you remove all your glycerin that forms, and water washing usually takes care of that. So usually we find that people who are home brewing usually have no problem with any free glycerin still left in their fuel as long as they wash. Commercially, they do washing in a slightly more constrained. They use a lot less water than home brewers do, so they don't usually. They sometimes have free glycerin present, but it's really not really something that will remain if you have done the washing steps. But monoglycerides and diglycerides will still be in your fuel. Another contaminant that's formed during this reaction is soap. And that's a side reaction that always happens no matter what we do. You really can't prevent there always being at least some soap formed when you make biodiesel. And that's because the chemistry of making soap, for example, old-timey hand soap that people make as a hobby a lot. There's the chemistry of that is very similar to what we do when we make biodiesel. So when we make biodiesel, we use lye, we use sodium or potassium hydroxide as a catalyst. And the problem is that that catalyst sometimes also likes to react with some parts of our oil and make soap. And it's actually specifically soap, the catalyst, the sodium or potassium hydroxide. When it goes on to being an ingredient in soap making, it's reacting with the fatty acid part of the oil molecule, which is actually, what we want for our biodiesel process as well. But it'll react with it and not make it usable, so you'll see a loss of yield if you really make a huge amount of soap because you're actually turning some of your oil into soap instead of turning it into biodiesel. Soap also has actually I'll go into what problems these things cause in a minute. But so essentially there's a reaction that happens where water basically forms what's called free fatty acids from oil, which is when you just chop off these fatty acid chains, and they're really reactive with certain things. And they're very reactive with sodium or potassium hydroxide, and they go on to making soap, and they make water, which actually then goes on to make more free fatty acids potentially, like under some conditions. So we really try to usually minimize soap making by trying to minimize how much water is present in the first place. Like on the waste vegetable oil specifically, there's often water in it, and we really want to minimize how much of that is present. So that's another side reaction that we just can't avoid most of the time. Even if you work with even if you work with oil that really didn't have any free fatty acids in it to begin with, from the way that waste vegetable oil does. So even if you start with new oil, you'll still have a certain amount of soap that's formed for various reasons. Soap is something that homebrewers often become very concerned about because when you're first starting to make fuel, you often have failures that are basically look like gel. Like you don't really have a liquid fuel at the end. You have some kind of a gel, or you have floating stuff that's a gel. So people tend to get very obsessed. Or for a long time, people tended to get very obsessed with ways of reducing how much soap their reaction formed. And the main thing that they would realize is that if they cut down on how much lye was present, they wouldn't form as much soap. The problem is that the lye is there for a reason. The sodium or potassium hydroxide is there as a catalyst that makes this biodiesel reaction happen in the first place. And the more catalyst you have up to a point, the better your conversion is going to be. So soap is kind of a separate reaction. It's a side reaction that's going along. But if you try to, if it somehow gets rid of a lot of your lye, then you will not have the lye present as a catalyst for the triglyceride to biodiesel reaction. So we do really want to make sure we have enough of it, and that we don't. And that's really the only place where in this process, like making sure that you don't skimp on lye in order to avoid the soap making reaction is kind of important.
Is there something you can do to pre-treat to bind up all the free fatty acids before you introduce the lye?
There's another process where you can turn free fatty acids directly into biodiesel using a different catalyst, but it's not really. That's kind of a pre-treatment. So there are many biodiesel processes out there. I want to kind of talk about the most common homebrew techniques, and that's usually not done by homebrewers. Dave.
So the free fatty acid, is that present in a greater or lesser degree depending on how the oil was treated or what type of oil it is? Or
yeah, free fatty acid actually doesn't have much to do with the type of oil. There's kind of there are a lot of myths on the internet and out there in the homebrew community about different aspects of the process. And one of the ones you might hear about is people often say animal fat is high in free fatty acids or stuff like that. It's not really necessarily true. But free fatty acids come from, in waste vegetable oil, they come from the cooking process. So if the restaurant hasn't changed their oil that much, there's going to be, what you get out back is not really oil. It's oil and free fatty acid, which are, which you can't filter out, and which interferes with your reaction by making soap out of your catalyst. So that's kind of where that comes about. But also if you do wind up making a bunch of soap, it will actually set off a reaction where it begins to kind of destroy your oil and turn it into more free fatty acid, and then make more soap out of it immediately. Yeah.
In Bob's talk this morning, he talked about the total glycerol output dropping due to washing.
Yeah. Glycerol is water soluble, so you'll be able to wash it out.
No, he was talking about monoglycerides and diglycerides dropping as well some. And I wondered if you think that happens in homebrew.
No, that was an unusual. That was an anomaly, and there's a reason for it. But it's not. For all intents and purposes, monoglycerides and diglycerides don't get washed out. Soap and free glycerin do. Other contaminants. I kind of just want to do a little bit of an overview of the process and then go more into depth about this. Other contaminants in this process are that we use a lot more methanol than actually gets consumed by the reaction. And at the end of the process, what we'll actually have is biodiesel, glycerin, and methanol. And so there's often a big concern in homebrew land about, is it the methanol that's eating my rubber fuel lines? And which is actually kind of isn't really true. But we usually wind up, when we water wash, in order to get rid of the soap and the glycerin, the methanol goes away as well. Obviously, you guys all are familiar with the methanol recovery talk, at least based on the description in your conference handout. But Maud and the St. Louis group were doing the methanol recovery presentation, and so they basically take this extra methanol away. That's where the methanol that they're removing comes from. It was an excess. It was a larger amount that we had put in on the input end that winds up getting left over as a contaminant on the output end. And the reason why we have to do that, the reason we wind up with that situation, is that oil and methanol reacting to make biodiesel and glycerin is actually a reversible reaction. So there's a few different ways in chemistry that they handle reversible reactions, and one of them is to give you extra of one of the ingredients on the input end, which makes sure that the more difficult ingredient to react will more completely turn into a product. So that's what we're doing here. There's another couple of strategies that could be done. So there's basically we've got three water soluble so far. We've got methanol, soap, and free glycerin, and those can all be washed away. There are lots of tests for all those things, but they're basically not hardly anyone in small scale production really worries about them. The only reason you really need to know about soap is really more for fine-tuning your process. If for example, if you start washing and you find that it requires really large amounts of water, or if you're having stuff dropping out, there's a few steps in the washing process where you may have problems, and you can do a test for soap on the fuel and see if the soap is the problem. But in general, we never really test for soap to see if the biodiesel is ready to use or anything like that, or if the biodiesel is good or not. Because as long as you follow a standard washing process, it sort of leads you into getting rid of all the soap. There's no real way to do it halfway without putting a lot of heat energy into drying the washed biodiesel. So normally homebrewers get way more soap out than they really need to from your vehicle's perspective, and they get way more free glycerin out than commercial producers do. So usually those things we just don't really test for because they're not that important. They go away if you do the process right. Diglycerides and monoglycerides don't normally wash out, so it's really difficult to you really kind of do want to test for those if you're trying to fine-tune the process, and so that's not that's not something that you're going to be able to fix in the wash. So I want to go back to this reversible reaction idea and sort of talk about why the different ways of dealing with it, because they actually directly relate to both testing and correcting for high diglyceride monoglyceride content. So biodiesel and glycerin will react backwards a little more slowly than the oil and methanol do in the forward direction, but they will react backwards as long as you're stirring, keeping them stirred up, because glycerin wants to separate from biodiesel, but as long as you're keeping them in contact and you have the catalyst present. So if I had this catalyst gone, if I took this, this is a bunch of this is some commercial biodiesel that I just bought. It's supposedly from Often Petroleum. But this is washed, and if I were to stick a bunch of, pharmaceutical grade glycerin in there and then mix them up, it wouldn't change a thing about this being biodiesel. They would not react. But as long as there's lye present, they would, and they could actually react backwards, and you can go back from being, from having a bunch of biodiesel and a bunch of free glycerin to having monoglycerides or diglycerides or triglycerides. So you could basically unmake your biodiesel if you aren't careful. The thing that inhibits that process is the presence of extra methanol on this side. So essentially, there's in equilibrium reactions, there's basically a limiting factor, like a limiting product or a limiting ingredient on either end that will prevent the reaction from going in that direction. If you've got, past a certain point, you really reach this point where you reach equilibrium. If you have a certain amount of oil, you have some oil and you have a certain amount of methanol, you may wind up making it'll proceed in the direction of making biodiesel until you have a certain amount of glycerin, at which point it will stop turning the rest of the oil into biodiesel. And the same thing happens in reverse. If you were trying to react some glycerin and some biodiesel in the presence of lye, trying to react it backwards, it'll make some methanol and then it'll make diglycerides, triglycerides, and oil. Once it has made a certain amount of methanol, then that starts reacting the other way, and after a while they just kind of balance out. They reach this equilibrium point where you can't get it to go in one direction or the other any further. So again, I already mentioned that the way that we push it further into being biodiesel is we add more methanol than we should need if we looked at it on paper. So if you did this not in cartoon chemistry, you could calculate how many moles of methanol you need to react how many moles of vegetable oil and how many moles of biodiesel that will make. But if you just added that quantity, that mass of methanol, it would never actually make just biodiesel. So the one strategy is, we add extra methanol. We use close to twice as much methanol as we actually need. A lot of the time, or commercially, they use almost close to twice as much. But in home brewing, people tend to want to skimp on methanol because that's the most expensive ingredient. So a lot of the time in the homebrew process, there's kind of a compromise that's reached. Like we have extra methanol so that we can get the reaction to be more complete, but we are cheapskates, so we don't use quite as much as we would want. And so the other process for dealing with getting your fuel to be more fully converted into biodiesel, to have less oil or diglycerides or monoglycerides left, is to do what's called to react it stage-wise, which basically means that if you take away this glycerin halfway through the process and then just keep on adding methanol, it'll make your oil into much more completed biodiesel than if you tried to do it all in one go. And so what we do when we do that is we commonly do what we call the two-stage base reaction, which means that we calculate how much catalyst and how much methanol we need to use in order to react a certain amount of oil, but we don't add it all at once. We add about 80% of it, and that's actually enough to get you to drop a bunch of glycerin out of this oil. And what you'll have is glycerin and then partially converted biodiesel, or biodiesel with a bunch of partially converted oil in it, like monoglycerides, diglycerides, triglycerides. And if you then took that glycerin away and then added the remaining 20% of your methanol and lye, then you will get that oil to turn. You'll get much better conversion. So when they talked about conversion in Bob's talk this morning, or you may have heard that bandied around at the conference. That just refers to what percent of your oil actually turned into biodiesel rather than any of the other stuff.
So just to kind of clarify, that's because you've got the two limiting factors, one on both sides. Because you're taking out almost all of the limiting factor on one side, and you're not taking it out of the other side yet. When you do the 80-20 and you do the 20, then the limiting factor on the other side is kind of gone, which is why it becomes a little more complete. Yeah.
This way. Yeah.
Okay.
So
The molecular partial pressure of the glycerin drops so low that it can't react back the other way.
Mm-hmm.
So the 80-20 process is actually a really good one for just to use as a standard process when you don't really test your fuel. In Bob's talk, so for those that don't know what I was referring to, Bob Armitrad did a talk about testing for monoglycerides and diglycerides basically this morning. He was talking about how they do it in the lab, which is pretty expensive. And so for those that don't have access to a testing method, so you don't have any feedback, you don't get any visual feedback when you look at your fuel. We actually don't know whether this is really good fuel or if this is full of monoglycerides and diglycerides right now. So if you don't have a way of testing it, then a good insurance is just to divide your methanol and do your methanol and catalyst addition in 2 stages. So add to 80%, retract the glycerin, add another 20%, retract the glycerin again, and then keep proceed on with the rest of your processing, which usually involves adding water in order to draw out the water-soluble contaminants. And that is pretty much guaranteed to get you way better conversion than if you did it in one step. Iowa State University did a bunch of work on that, and I think they were finding that the degree of conversion, like the extent to which it converted, was about an order of magnitude more than if they did it in one stage. So they were going from if the standard says that the amount of standard has a number called that's 0.24% glycerin calculated from the bound glycerin that's in that the machine sees, the gas chromatograph sees. They were seeing 0.024 by doing 2-stage process on new oil. So it's really good, kind of a real good insurance.
How long do you leave it between one stage and the next?
An hour, not very long.
Not very long.
Yeah,
Second
half an
stage.
hour to an hour. I'm sorry, second stage you leave it to settle overnight until you get to it next.
Okay, good.
Yeah.
There's a stupid question that's just begging to be asked. If an engine will burn straight triglycerides.
I haven't gotten to that yet. So I'll cover that in a moment.
All right.
Okay, and so that's pretty much like your 2 options basically for making sure that you have good conversion, regardless of how you test for it or if you care about it. But the 2 options that are out there are that either you have to add lots and lots and lots of methanol. There are 3 options. You have to add enough methanol. Adding enough catalyst is really important, or doing the process in 2 stages. But that still means you still need to do the right amount of methanol and catalyst. But it's just kind of extra insurance. The 2-stage process would be extra insurance that you would make get better quality conversion. And the role of catalyst. So the catalyst is there to I already said to break up to allow this reaction to proceed, to allow you to actually break off the fatty acid chains from the triglyceride molecule. And in home brewing, people have generally been working without any real feedback on what their process is. There have been a lot of kind of very ineffective tests that were out there in the past, so people sometimes had false feedback. And so in the distant past, home brewers often they were kind of just shooting in the dark. They were looking at the fact that they had a tendency to form gels from the soap side reaction. And so they realized that if they cut down on how much lye was present, then they wouldn't form that gel, without having any way to tell that they were also making poorly converted biodiesel. So a lot of the time there are a lot of home brewers out there who just aren't using enough catalyst as well. The reason they don't use enough methanol sometimes is just because they're trying to cut down on how much it costs. The reason they're not using enough catalyst is because they're trying to avoid soap production, which is actually not a good strategy, because there's the importance of the catalyst to catalyzing the biodiesel reaction is greater than the drawbacks that come about when it makes soap. Let's go to other contaminants. Those are the contaminants that are formed. There are some that can be formed during storage that I'll go into a little bit later. I want to talk about what effect these contaminants have on vehicles, on engines, and why it's important.
Is there a test you can do for the amount of free fatty acid?
Free fatty acid is the titration.
Oh,
that we
it is,
do.
okay.
Yeah. Obviously, if you have a big soap gel in your fuel tank, which can happen if you don't wash. If you have coated fuel filters and you're burning the stuff that doesn't burn completely, so it can lead to clogged injectors and slightly clogged injectors, and you may not really realize it's happening, but that can eventually cause you some engine wear. Soap won't burn completely and it'll form an ash that's somewhat abrasive, so there's a big concern about how much soap is in. One of the reasons that it's standard practice to wash the soap away is just concern about either this abrasive gel or the possibility this abrasive ash that's formed when it burns, or the possibility that it simply gel up in your fuel tank. One example is that I've seen I've run unwashed fuel somewhat. I did a bunch of it while driving cross country a few years ago, and I did wind up with clogged injectors. And it may have been the soap, or it may have been the free glycerin that was on my unwashed fuel. But there's also there's a lot of junk on my filter and a lot of junk on like sensors in the fuel system that probably is mostly soap that is just getting stuck to certain sensors. And so there are some engines that are more sensitive to that than others. For example, like GMC 6.5 diesels that were really common for about 15 years. They're real sensitive to that. They have an optical sensor that gets fouled by soap or fouled by glycerin. So it's better insurance to just wash. The other thing you can do if you don't want to there's a few other alternatives if you don't want to do the water washing, and they also will get you to the same point of not having that material clog up injectors or fuel filters or any sensors. And that's just one of those alternatives is just to let the stuff settle long enough. Like if you let your fuel sit for several weeks, it will a lot of the soap will settle out. You don't use the bottommost portion, but it's kind of, in some ways it's easier than washing. Depends on how much land you have. If you got space to just place a whole bunch of drums of fuel out back, that might be a way to avoid having to deal with a wastewater stream that you may not have a way to deal with. So other vehicle, and that also takes care of free glycerin, which I guess I should go to next. So when you have free glycerin, which is the brown stuff that settles to the bottom of the container when you make biodiesel, it's water soluble. It doesn't burn well at all, and it's kind of gooey at times. So it doesn't. If that starts going through your fuel system, that really usually doesn't burn well. And again, when you in an engine, when you have that will also lead to like a gel that happens to be abrasive. Which is something you usually really don't want in your fuel system. And so that's the only challenge as far as quality control. That's the only challenge with using Magnesol is just not either making sure you use enough of it, or making sure you filter it out at the end, so the fact that it's abrasive doesn't go through your delicate fuel system parts. And the other contaminant, so glycerin and soap sort of have a similar effect. Glycerin just really doesn't. It's really just even stickier. There's much larger amounts of it possible than the amount of soap that's in your fuel. When you let your fuel settle after making a sample, you pretty much will see, if you're doing it in a small jar, you'll see large amounts of it settle out under the fuel within about an hour. And unfortunately, it'll keep on settling for a really long time, like weeks. So you can't just instantly, assume that it's all gone just because you saw it. So the big concern about unwashed fuel, about fuel that hasn't had glycerin removed from it fully, is that if you put that unwashed fuel into someone's fuel tank, after a while they'll start getting a layer of glycerin on the bottom of their fuel tank. And after a while, that can get high enough that your engine actually takes a gulp of glycerin, which is really bad. Like that will really cause major clogging, coking. It does tend to coat fuel filters, but it also goes through them. So you could get, depending on like how cold and hot it is outside, or what type of catalyst you had used, or meaning what type of ingredient was part of the soap. The soap that you form usually winds up in the glycerin, and that makes it even thicker if it's made from sodium hydroxide, and that will sometimes form like an immovable gel, but a lot of the time it'll be something that will partially clog your fuel filter, so you're eventually kind of starving your engine for fuel, as well as go through and then not burn completely. So that's when that's when you get various kinds of smoking due to clogged injectors. I found that a lot of people that have dealt with problems from those two contaminants that have clogged injectors just haven't noticed. A lot of the time, people doing experiments where they're cutting corners are sometimes just playing around with older vehicles, and they kind of have this assumption that it smokes, and like that doesn't necessarily have to be the case. And so, a lot of quality control problems with making biodiesel will result in fuel that will still run in your vehicle short term, and then it might cause some sort of lowered fuel system life. Like clogged injectors usually just means that you may wind up having a hard time cleaning off the carbon, and eventually need to replace your injectors if you really bother to look. But it can also cause some other problems that are much more serious. So one of the I'm kind of do my little engine diagram here for cutaway engine diagram. So cartoon mechanics. So just a really, really simple diagram of like a big direct injection engine that has a combustion chamber and the piston that goes up and down in the combustion chamber, and an injector. So this is like the injector that is basically sprays fuel into the combustion chamber, which then powers the piston when it ignites. And the spray pattern is supposed to be a bunch of, basically a mist, a really fine mist. It's supposed to atomize really, really finely. When you start clogging your injector tips, a few different interesting things happen that can cause more serious problems besides just needing to replace your clogged injectors or clean them. So if you let it go long enough and it gets clogged badly enough, you'll start spraying large droplets. And the same thing will happen if you're trying to burn a fuel that's too viscous for what the injectors are designed for. So one of the reasons that when people run their vehicles convert their vehicles to run on straight vegetable oil, one of the reasons why generally that involves heating the oil in order to make it less viscous or less thick is that if you were to just spray thick vegetable oil into the combustion chamber in most vehicles, you're going to get incomplete combustion because you've got really big droplets. Combustion or burning happens from the outside in. When you have a droplet of liquid fuel, it's the reaction with oxygen is happening on the surface. So if you've got too big of a droplet coming out of your injector, and then even if it catches fire, it's not going to burn. If it doesn't burn down all the way before the next stroke of the engine cycle happens, then you may wind up with coating that may be taking place all over your cylinder walls or your injector tip. And so essentially, it sets off a process that's like
Reinforcing.
Self-reinforcing, yeah. That's not what I meant, but yeah. Self-perpetuating, thank you. So it will basically make a worse, create a worse clogging condition. So if you may start out, so if you have either you start out with injectors that are somewhat clogged for some reason that having to do with your fuel not burning really well, for example, having glycerin in it, or soap in it, or once it starts clogging a little bit, then if it it can make the whole condition much worse. The next step of damage that can happen is that you'll start kind of spraying a big spray of fuel, or maybe part of your injector is still emitting mist, and then the rest of it has a big stream coming out of it. Well, diesel engines are not designed to run on a stream of liquid fuel in the engine, in the combustion chamber. You really need to have fine mist for it to burn that fuel completely. And and again, it'll just do a feedback loop. If you've got a spray, if you've got a bad spray, it'll just clog it further. Well, once this not fully burning fuel begins to get on your cylinder walls, there's a few things that can happen. One of them is that if there's a spray happening, it can actually run past your piston rings. Your piston rings act as a gasket. They're there to keep your fuel and the flame away from your motor oil, and vice versa. So if you got liquid fuel that's getting past your piston rings and it gets into your motor oil, then you start getting contamination of motor oil. And two things happen. First, the fuel will first dilute the motor oil, so it doesn't do its job well because it makes it too runny to really lubricate properly, to stick to the surfaces like it's supposed to. Next thing that'll happen is kind of specific to vegetable oil fuels, or it's worse with vegetable oil fuels, which is that vegetable oil or biodiesel will actually thicken up after a while. They'll do something called polymerization. And if that's happening in your motor oil, it'll polymerize your motor oil. And what will happen at that point is that your motor oil circulation system can't move oil around, and it does not act as a lubricant. And it can even get bad enough to the point where you actually have what looks like big plastic rocks in your oil pan. And those are not circulating up to your valves, or anything like that. So it's a very serious situation. It can happen on diesel, but it's much more likely to happen. The polymerization is much more likely to happen on vegetable oil-based fuels. And it's kind of more likely to happen on straight vegetable oil, but it has been seen on biodiesel quite a bit. And that's kind of something also to just watch out for with like older engines, because if you have worn piston rings, that'll be more likely to happen. Anyway, so that's one of the issues that can happen. The other one is that you can get carbon just on your cylinder walls, which can also damage piston rings eventually, or it can get into the piston ring glands and cause problems. But that's sort of the concern about trying to get fuel that burns well. So usually biodiesel will burn really well, but if you have it contaminated with a large amount of glycerin or a really large amount of soap and your glycerin, you haven't washed it, that's one of the concerns. Monoglycerides and diglycerides are also somewhat thicker, and I'll go into more of that in a second. Peter?
Another potential problem there as well is some of the pistons are slightly thinner, and you actually end up getting a hot spot on your piston head, and it actually burns a hole through your actual
So that's kind of worst case scenario. It doesn't happen to most people, but it has happened. I think all of this stuff is actually a kind of a worse situation with agricultural slow-speed, like stationary engines. So, for instance, there's a lot of research that was done badly on straight vegetable oil, where they basically destroyed a whole bunch of engines that would have powered water pumps or generators, and that basically are a very different situation than what you see in an on-road vehicle. I've seen problems with poor quality biodiesel, where we got all kinds of clogging and coking and smoke that we couldn't. That was really hard to get rid of because it was actually in the cylinder head and not just we didn't want to pull the cylinder head and scrape everything, but it wasn't just the injectors, and that was a generator situation. So it's something that just sits there and idles all day, which is much more prone to problems than those of you with Mercedes that are going to be driving down the highway at 80 miles an hour. I saw a hand up there.
Okay. I was just going to a little comment though. These problems aren't problems that are going to show up right away though,
Yeah.
right? Like this isn't like if you put one bad
No.
in, you're not going to notice this. Right?
Most of the
This is
time, no. Yeah.
prolonged, right?
Yeah.
Okay.
If there's most of the time. So I'll go to another one. Was there one more hand? I think you had.
When you do have that buildup of crud, how do you get rid of it other than mechanically scraping it out?
Well, I mean, there's what they call the Italian tune-up, which is to take the thing for a spin really fast. And put good fuel in it and drive it fast for a while. There's also injector cleaner. I think there's various kinds of like combustion aids that they sell as like injector cleaner. But we couldn't do it with a generator. That may just be because you can't rev it. We loaded it pretty good. We had it revving real high. That was essentially a little truck engine. It was like a Isuzu engine.
Do the injector cleaners work when added to biodiesel, or?
Yeah, totally. But I mean, clean biodiesel is usually an injector cleaner all by itself. But when there are things contaminated, it'll act against that element or something.
Good idea to keep the oil change, especially on the
Yes.
car.
Absolutely.
Are these problems that you're talking about with buildup in the cylinders and injector clogging, those are associated with too much mono and diglycerides?
They can be. Yeah, they're much more associated with having a lot of glycerin in your fuel or running blends of like oil where it's drastically higher viscosity than what the engine is designed around. So that's really like specifically, most of the time that's really problems with situations where you have stuff drop out of your fuel, which is usually either soap or glycerin or both, or possibly magnesol or other things that you've added. But because anything that won't just spray as a nice liquid if that's anything that's kind of a gel won't spray as a nicely like diesel is supposed to. But the monodiglycerides, there's some debate about exactly what effect that has, and I'll cover that in a second. Sam.
Are you familiar with problems from using really hard water in your wash process?
Yeah, so I guess there's another couple of things that can happen if you do your water washing in order to remove your soap using really hard water. You can get insoluble soap formed, and that can be in your biodiesel, but usually that falls out. It's usually it's the white stuff on top of the water that people sometimes see in really small quantities when they wash really well.
And would that get pulled out with like the amber-like stuff?
I don't know anything. I don't really use magnesol or amberlite, so I don't know how that works.
What about copper ions if you have copper tubing in your process lines?
Don't have copper tubing in your process stuff. Simple answer to that. That's really not a practice that most people do. People abroad may have that problem because sometimes there's you can't get non-copper water heaters and like tanks. Some common tanks in England, for example, are copper, but we don't really have that problem here.
But even the brass valves have some copper.
Yeah, it's don't jump ahead of me here. So let's talk about what effect where monoglycerides and diglycerides fall in this whole picture. So I'm talking about a couple of things that are water soluble. They're fairly easy to get rid of. I guess I skipped methanol. Extra methanol left in your fuel is not really not that big of a deal. Like it's corrosive in its pure form. We've got a real small amount of it left in biodiesel. If you had a way of getting soap and glycerin out of your fuel, the methanol that's left over probably isn't all that bad. Like there's just not that much of it. So we normally don't, but we don't really concern ourselves with that because as long as you wash, all this water soluble stuff goes away. There's another thing.
What did you say about hard water? What is it called?
It causes. Okay, well, if you're washing with hard water, and it contacts soap, it can actually cause. It causes ion exchange, which can produce something called insoluble soap that does not wash away. But it's visible, like it's something that you would, if you
scale on your shower wall?
It's soap scum, so essentially. You wouldn't want that to go through your system, but usually when people see it, even if they don't know what it is, they leave it alone. Peter.
Yeah, we've done a lot of work with the fuel major companies and so forth, and as well as the motor manufacturers, and they're actually not particularly concerned about the small quantity of methanol left.
Yeah.
They say it actually even assists with the combustion process, so they're not really concerned about it at all.
It's fairly small. But it's just something that it was worth mentioning the methanol concerns because people do. There's just a really widespread myth in home brewing that the methanol is the part you have to wash away, and the moment people discover that you don't need to wash the methanol away, then they say, why bother washing? Well, it's the glycerin. So can I just move on and cut the questions for a moment so I can get through the where we're going with this, because it may answer if someone knows. So diglycerides and monoglycerides, normally they're oil soluble. I can almost guarantee you, knowing how this was made, that this probably has a lot. This is green biodiesel because it was made from hemp oil, by the way. But I can almost guarantee you that there's a bunch of monoglyceride and diglyceride in it. It's really pretty. It's really see-through. It's really liquid. It was made by Todd Swear in the Journey to Forever.
Was that before or after the smoke, by the way?
I'm sorry?
Was that before or after the smoke?
Translate English to English, please.
Was it smoked?
Okay, got it. Anyway, and I can almost guarantee that this is probably poorly converted because I know what process this person was following. So, but you can't tell by looking at it. And this stuff is commercial biodiesel. I can't tell by looking at it. We don't have a real good way of testing its viscosity or anything to tell exactly what is in it. Just from physical properties like thickness or thinness, thickness or runniness. So what's the problem? Well, monoglycerides and diglycerides usually are liquid and they're oil soluble, and most likely most of your engines that are out there are going to burn them just fine most of the time. The problem is that occasionally you get strange behavior either at colder temperatures or sometimes not at colder temperatures, but just kind of at random, where you develop crystallization of those monoglycerides and diglycerides. And that's the point where, I made some nice fuel, it's nice and liquid, I, sold it to my friend who stored it for a while in his garage and put it in his tank of his car and then it sat for a while. In fact, we had this happen to somebody in August, I think, or several years ago, so it was hot weather. Stuff sat in the person's car for 2 weeks, they came back and their car wouldn't start. And it turned out that there was this gel in their tank all of a sudden, and it was, and it just kept coming. They kept taking changing fuel filters, and all this dark gel kept coming out. They couldn't figure out where it was coming from, and it probably wasn't, tank cleaning. It was just there was something that had changed about the fuel. It went from looking nice and clear like that to having a big gel at the bottom. And that is a behavior that seems to be sometimes exhibited by diglycerides and monoglycerides, which is that they sometimes crystallize. Usually it takes kind of shocking it with cold weather to do that, but it may have been, where we live, it isn't all that cold at night, so in August, so it probably happened at 70 degrees, 70-degree nights or something. It was probably enough to make it happen with that particular biodiesel. And the biodiesel wasn't all that under-converted either. We had it tested, and it really wasn't, drastically horrible. It wasn't like the other, one of the chromatograms that Bob had. But anyway, that was actually enough to precipitate out monoglycerides and diglycerides. And it's kind of hard to get them to go back into solution at that point. You could, heat it up, heat the sample up, and maybe they'd go liquid again and stay that way. But it's not something that usually happens in my experience, at ambient temperatures. It's usually, you have to really get past a 100-degree day to do it. And there's no guarantee that on the underside of your vehicle in the fuel tank it'll actually get that hot. So that seems to be why people try to avoid low conversion fuel. That seems to be the biggest issue. It's just that when you actually do see catastrophic problems, it seems to be linked to this crystallization behavior. And I've yet to see any data on what happens if it doesn't crystallize. If this stuff, monoglycerides and diglycerides stay liquid and they move right on through your fuel system, it seems like at most, at warmer temperatures, it doesn't seem like there's really much of a documented problem. I haven't seen any studies where they've really looked at that either. There is some concern, from engine manufacturers that poorly converted fuel may clog injectors, but it doesn't seem like that usually happens as long as they stay liquid. The easy assurance is to just make sure the stuff is fully converted by doing that two-stage process that I was talking about, where you the two-stage 80-20 method. And the type of fatty acid composition that you have generally affects that property also. If you have biodiesel made out of animal fat, it'll be and you form monoglycerides and diglycerides, they'll be more prone to crystallizing than if you used like something high in oleic acid, like soy oil or olive oil, that made it from an oil that tends to be liquid at room temperature. Basically, the properties of the oil will follow on through this whole process. If you have like fatty acids that come from a lard, it'll tend to make a more solid and thicker monoglyceride, diglyceride, even and a biodiesel that'll somewhat more resemble the original fat in terms of how it reacts to cold weather, for example. So usually, I think we see this kind of crystallization thing happen more with like more saturated biodiesel and monoglycerides and diglycerides that have been made from more highly saturated fats, but that's not always the case. I've seen it with, we had a 250-gallon tote of it that we bought from a home brewer who wasn't doing a very good process, and it crystallized, at not very cold weather, and they were working with purely liquid corn oil, and that had happened. So it's kind of seems really unpredictable, and there's just not much you can really state about what will cause that behavior to happen. So that seems to be why we have such a push in the industry to why the national standards for what biodiesel composition is supposed to be all state that it has to be really well converted. Another point I want to make is to kind of point to this and talk about once again about the gas chromatography testing that Bob was talking about this morning. When you get a result, when you send the sample to a lab to get it looked at in terms of how much monoglyceride and diglyceride is in it, all they really tell you about is the glycerol backbone part of those monoglycerides and diglycerides, which doesn't look like much. So you look at the standard, and they're talking about 1/4 of 1% glycerol from monoglycerides and diglycerides that's allowed maximum to be in your fuel. And so everyone looks at that and they say, how could 1/4 of 1% possibly damage my vehicle? Because that just doesn't look like much contaminants. So I bet if you go to a diesel, throughout your vehicle's life, when you go to the gas station, you buy petroleum diesel, a lot of the time there's going to be more than 1/4 of 1% gunk from the fuel tank in there. And like petroleum people will tell you the same thing. There's all kinds of contaminants in the gas station underground tanks. It'll certainly be larger amounts than 1/4 of 1%. Well, they aren't actually counting a total amount of contaminants that's only 1/4 of 1%. Because the test, for some reason, they decided to do the way that they're doing the test. For some reason, it really only measures the glycerol portion. It doesn't report numbers in terms of percentage of like the total mass of monoglyceride, diglyceride, triglyceride contamination in that fuel. So it's just kind of essentially like you may be dealing with several percent or maybe 10% or something, some somewhat high numbers when you see that crystallization behavior take place. I've seen it where I have a sample about that big. There's probably that much crystallized junk in the bottom. And I don't know if it entrains other material in, or if that's just what volume those crystallized monoglycerides and diglycerides take up when they do that kind of unpredictable behavior. But it is enough that if you've got your vehicle, if that builds up to the point, if that's happening in your tank, then your vehicle is trying to spray gel through its injectors, and then again you start with this whole process I diagrammed here, where you've got large droplets because you're spraying something that's no longer liquid, and it doesn't burn well for that reason, and you can start getting clogging. I also have seen a lot of clogging that's caused by that, in addition to clogging of injectors that's probably just caused by not washing. That can certainly happen from like crystallized monoglyceride and diglyceride. Question.
So if you looked at your GC test and all of the glycerin was in the form of diglycerides, that would be much worse because the total amount of contaminant that represents is almost twice as much by mass.
Yeah, I don't actually know how much it is by mass. That's what I actually.
But it's almost twice as much because the glycerol. I'm saying the glycerol molecule is much smaller than the fatty acid, so it would be.
In some oils, yeah. So exactly.
In all of them, it's much smaller, and some of them it's a lot smaller.
Mm-hmm. Yeah.
So.
I mean, I would really love to get an answer on like exactly what percentage, like what the range is. But anyway.
Yeah. But diglyceride should be worse than monoglyceride.
Yeah. So I've kind of like hopefully hammered in why I think that stuff is important. Jennifer.
maybe I was kind of spaced out a little, but what is the, I just want to know if I ever see this, what does it look, what does that gel look like and that you see when it drops out? You don't have a sample?
I didn't bring a sample of our molar shape. It's lighter, it's usually lighter and sometimes darker, and I don't know if when it's darker, maybe there's something else going on.
But it's thicker.
It's thick and it looks
Is it
exactly
plastic?
like,
Yeah.
it looks exactly like the beginning of freezing in biodiesel, if you're familiar with what that looks like. So it becomes very difficult to diagnose because if it happens, if it's winter, and it is more prone to happening in colder weather, then you might just assume that your fuel has a high gel point, and that can totally happen. It's really hard to predict, like if that problem happens, it's really hard to tell if it's due to monoglyceride, diglyceride, or just due to high freezing point or high melting point biodiesel. So it's kind of tricky, but
What I saw in some fuel, it's actually commercially sold fuel, was like a layer of white stuff on the bottom. I don't think it was Magnusol because it was kind of fluffy, and they were saying, I talked to them, they were saying that they thought it was probably monoglycerides from what they were saying was reversion because they're trying to reclaim their methanol by heating under pressure, and they were saying that it's probably pushing the reaction backwards and forming some maybe diglycerides.
Yeah. And that's the order. That's kind of the order in which like if you do have reverse reaction in the scenario he's describing, that's exactly what will happen. Is first it'll make dyes and then tries and then maybe make oil, but you do, that's exactly what will happen. Okay, I'm sorry, you had a hint. No,
For that reason of reverse reaction, would you then not want to try to recover the extra methanol in biodiesel?
No, there are ways to. You basically do the recovery process quickly. That's kind of outside. I kind of don't want to go into that, especially timing wise. Dave, again.
You mentioned using very hard water is for your wash is not such a good idea.
You know what? Let's not worry about that because that's actually not that big of a problem. It causes a visible. You still wash the soap out and you get a little bit of scum in the bottom of your tank. Nobody puts that scum in their car. It's really visible, so it's not like I've never heard of that actually being a problem for anyone other than that they just don't use that stuff and they compost it. I want to go on to talking about testing for monoglycerides and diglycerides in terms of in a homebrew setting. So the cool thing is that if you start out with we kind of do the same thing when we do the 80-20 method. You start out with triglyceride and you mix it with some methanol and some catalyst. You can break up all these fatty acids and go through this whole process and eventually wind up in biodiesel. Well, if you start out with a diglyceride, you can also react it with some methanol and some catalyst and it will become monoglyceride and then a biodiesel. So it doesn't matter where you start. It doesn't matter if you start out as oil or if you start out somewhere in one of these other processes. It's still basically the same reaction. So it doesn't matter if it's like triglyceride, meaning oil, or diglyceride or monoglyceride. So we can use that to our advantage in a couple of ways. One of them is to, that's part of what makes the 80-20 method possible. If your 80-20 method, if you only added 80% of the amount of the ideal amount of methanol, and it hasn't converted your oil completely, well, the remaining 20%, once you remove the glycerin that inhibits that reaction, remaining 20% of the methanol and catalyst will start eating the diglycerides and monoglycerides. And work on them. And so we can use that as a test, and that's kind of one of the older tests that people have used that allows you to test for the presence of monoglycerides and diglycerides. And it's really crude. It's just not all that effective, but it does tell you something. It does tell you about when you have a lot of the problem of the contaminant present. So basically it's a reprocess. It's what we call the reprocess test, and that is basically taking the crudest way to do it is a liter of oil, and you add about 50 milliliters more. A liter of washed biodiesel. You add about 50 milliliters of methanol with about another gram of lye dissolved in it. And that, if you see glycerin, you just process it the way that you would have the oil initially. And if you see a lot of glycerin, or if you see any glycerin fall out, then you have really bad conversion. It's actually like, it looked like a very small amount of glycerin, but it actually correlates to fairly poor conversion, I believe. Usually, there's a couple of problems with that method, and that make it not all that exact, so you can't really read too much into it. One of the problems is that because you're still going to be using more methanol than it actually reacts to break up all those diglycerides and monoglycerides, just because you have no way of knowing exactly how much to use. So if you use too much, one of the things that can happen is that any glycerin that you form which you're looking for as a visual indicator. Some of it might just be up there floating in the fuel, and it might be several weeks before it drops out. So that can make it kind of difficult to really get a reading. You can get a kind of a false negative on that test. So if you're looking for it to not drop any glycerin because you're hoping that your fuel that didn't have much monoglyceride and diglyceride to turn into glycerin, if you do the reprocess test and there was actually a lot of methanol floating in there, it'll make that glycerin. It'll just be suspended in the biodiesel layer, so you won't see it. And the other issue is just that it's not very sensitive. Like if you have fuel that is mostly biodiesel and a little bit of monoglyceride, diglyceride, it won't drop any glycerin that won't settle. So there's been a few recent innovations in quality testing and homebrewing. One of them is that someone on the Infopop biodiesel forum, like biodiesel.infopop.cc, someone on that forum figured out that when they do a reprocess test using sodium hydroxide, so this does not work with potassium hydroxide. You have to have standard, drain cleaner lye or sodium hydroxide. You work with that. If you do a reprocess test and you use sodium hydroxide, it will actually potentially give a more sensitive indication of high conversion than the glycerin test with nothing falling. Than the reprocess test with no glycerin falling out indicates. So if you have a reprocess test and you see glycerin falling out, then you know you have poor conversion. That's fairly significantly bad. If you have a reprocess test and nothing falls out, that doesn't tell you anything. It's not a positive. Doesn't confirm that you have good fuel. It just says that you don't have really bad fuel. And the innovation in the reprocess test that recently happened was that someone figured out that if you do it with sodium hydroxide, then if your fuel didn't have much more monoglyceride or diglyceride left to convert into glycerin, you may get a gel. Because what will happen is that you can make soap out of biodiesel. Like if you run this reaction on it, it's already prone to making soap, and you could actually make this reaction out of biodiesel instead of oil. So biodiesel and lye will make soap. And so in that modified reprocess test, he figured out that if you follow the proportions fairly exactly, and then you get a gel within a few minutes in your jar, in your sample, then there's a pretty good evidence that means that indicates that it was fairly high conversion biodiesel. We don't know exactly what the breaking point is, and I think that will depend a lot on what kind of oil you made the sample from. In the case of waste vegetable oil, you really can't tell because the wet vegetable oil is going to vary a lot in composition based on what was cooked in it and a few other factors. So that modified reprocess test seems to be a really good one. And then you sometimes get kind of hard to read results because sometimes the gel will happen but much later, and that's usually not to be taken as an indication of high conversion.
What about doing the reprocess test on unwashed fuel?
It doesn't work. It doesn't give you, so you need to have washed fuel in order to do the reprocess test. The unwashed fuel contains such a large amount of methanol that it inhibits settling, and it also inhibits gelling, because if you take soap and you add a bunch of methanol to it, it'll be liquid. So it kind of, the fact that unwashed fuel contains excess methanol will throw off this test completely. So we don't do that.
Can you use this test with the lye if you use the KOH to begin with?
Yes, The next test for conversion, there's a few other tests. There's one other one that's not really done by most people, which is that it's a viscosity test, and it's really it's actually almost like outside the scope of this talk because it's involved and hardly anyone does it. But there are a number of ways to test viscosity, and they use it for things like testing motor oil easily, or testing paint, or testing other viscous liquids. Which is essentially it's a container that has a little hole in the bottom. It's kind of a see-through container with some markings on it, and a little hole that's like a real small diameter. So you basically fill the container completely with liquid, and then you let it fall through the hole, and you time how long it takes to pass those two marks. And so if you have a thicker liquid, it'll go slower. It'll drain slower through the hole, and it'll take a longer time. And in the case of biodiesel, we can do that as part of a larger testing regimen, and you can use that to test for conversion. And you can actually get pretty specific and pretty exact about it, but it's more sensitive than the reprocess test, but it takes all day. Like you have to make your fuel, wash it and dry it, wash it and then get the water out of it, run it through the reprocess test. Run it through the viscosity test. Then take that same oil, take that same fuel and reprocess it turn any monoglycerides and diglycerides into glycerin, wash it all over again, dry it all over again, run it through the viscosity meter again, and at that point, you'll see any difference that happened from doing that reprocessing. So essentially, it'll tell you like exactly how much, or it'll tell you more about how much stuff you got rid of than just.
So the timing is relative, not absolute.
Yeah, I mean, it could be absolute if you knew exactly what kind of oil you were running, but you don't. You never do. So basically, that's another issue where the fatty acids become a problem. So most of the time, waste vegetable oil is made from. By the time it winds up as waste vegetable oil, sometimes there's animal fats in it, but a lot of the time most natural oils are not just one type of fatty acid; they're a mix of different things. So if you you can't assume that like a certain runtime means anything. Peter.
Yeah. Would it not be worth your while building up a table? So before you even had to go into your second test, you could almost build up data and just gauge from the first viscosity test more or less roughly what you're doing.
Yeah, I think there's just enough of a difference from one oil to the other. So okay, if you had for example, if you stuck with the same feedstock, so if you had one big vat of fuel and you made different batches out of it, then you could test them against each other. Otherwise, you're basically creating another batch so you have something to refer to.
You only get your oil always in the same place.
No, but it'll vary. It'll vary a lot it'll even vary from time to time. So you can't just assume that it's the same thing based on the fact that it's always soy oil or whatever. Because if they cook it longer, if they don't cook it as long, there's things like that that'll affect the date.
What's the units of viscosity?
Centipoise, which you're not going to get out of a homemade viscosity tester, which people usually use with a plastic bottle turned upside down with a little piece of copper and stuck in the lid. So, I mean, you can get more elaborate than that, but that'll actually tell you something.
I'm just wondering if you could like calibrate your.
Yeah, you can certainly. Okay, yeah, you can certainly measure the exact viscosity of a liquid, but the thing is that you have no reference to tell you what it's supposed to be for that particular oil because you never know what fatty acids are connected to that original oil, and there's like always a wide mix. So that's why.
Was your room temperature from your first test, if it happens to be later today?
Yes.
It has to be relative.
That's another big drawback of anything having to do with viscosity as well, is temperature sensitive matter.
The reprocess test and room temperature, or is that
the reprocess test, like usually for reprocessing, I don't usually heat anything. There's a bunch of reasons for that, but it's so crude that it doesn't matter, I think. Okay, next thing. So viscosity is another test that people do, but it's not that useful by itself. It's not like, I just went and bought some of this fuel at the pump, and it's not like I'm going to run a viscosity test on this and then say, oh, this is terrible, I would never put that in my car. Because I don't know, I have no idea what oils are in it, which would be what would have affected my viscosity test. So the viscosity test is only useful as part of a larger regimen of testing where you have, reprocessing, washing, and drying going on. And it can be more useful. If you had a sample of the original oil, you probably can you can fine tune it a little bit more, but not completely enough to really assign it numbers, I don't think. Another couple of tests that are available for monoglycerides and diglycerides. Recently, there's been a bunch of excitement about this methanol solubility test, which is that someone figured out that if you dissolve a sample of biodiesel in a sample of methanol, and if you control the conditions carefully so your methanol doesn't evaporate and you've got the proportions just right, if you see little beads of oil fall out, that's monoglyceride, diglyceride, and triglyceride related. And the proportions, I think, I haven't actually done this yet. The proportions, I was like scrambling around trying to find a glass vial so I could demonstrate it, but there wasn't anything I could grab here. The proportions are something like, does anyone remember this? I think it's something like 7 milliliters it's something like 3 milliliters of biodiesel and 27 milliliters of methanol. And you would actually do better if you upped the amounts a lot, like 50 and 20, 250. It's something like 50 milliliters of methanol in 50 milliliters of biodiesel in 250 milliliters of methanol. I think is probably a better way to do it. And that also you can find on the InfoPop biodiesel forum, so biodiesel.infopop.cc. And that seems to be working. That seems to be a lot more sensitive than just the soap gelling test and the. It's much easier to do than the viscosity test. So it's actually that's probably about as good as it gets as far as homebrew testing methods go. No, I think you kind of mix it in, and if it stays dissolved, then it's relatively high conversion, and if stuff drops out, then it's lower conversion. We don't know, and probably, most likely, temperature will affect it. In fact, we know that. Temperature will affect it. Water will affect it, so if your methanol has water in it, that will affect it. That's, there's going to be some effect based on the fatty acid profile of the original biodiesel's oil. And we don't know what, those are all things that we probably are not going to get really good answers on. That will mean, like, we probably can't say that when you get a pass or a fail, you're not going to be able to say that is like X% monoglyceride that caused that. Because X% monoglyceride in lard-based biodiesel will be different than like, than corn oil-based biodiesel, and you just don't know what mix you actually have in your waste vegetable oil. So that's probably a pretty good one. That's really new. That's just something that people have been playing with the last couple of weeks, and it's a really good thing. Was that okay? Let's see another hand. There's also another product that I do want to. There's actually one that I can show you. There's a product that just went on the market recently called the Flip Test, and that's spelled PHLIP. And maybe you guys could talk about it for a minute and that you can buy this from b100supply.com. He's selling it to home brewers. And that is these little vials of test solution that test for several things at once. And that is designed for helping distributors and fuel users like, people who are purchasing commercial fuel. It's designed for helping them kind of get some insurance against extremely bad fuel. And they cost about $5 a vial. Like it's about $50 for a pack of 9 or 10. And it gives you a vial of testing solution. So it's red stuff, and then you add some fuel to it. You fill it up to, I think, about equally. You fill it almost to the top, almost to the line on the vial. And you give it a few flips back and forth, and then you see what happens when they separate. So they sent, one problem with this is it's really hard to travel with it. It's just when they mail it, it sometimes gets, the reference test sometimes gets messed up from getting shaken too much. But here's the reference vial. I flew with this, and I had one break in the suitcase, so that's what I'm wiping off. But this is a reference test. So basically, like, here's what it's supposed to look like. There's really clear biodiesel that is separated from some really, from like the really red, clear reference solution. And if you put in fuel that has a lot of soap or a lot of catalyst, it'll probably it can actually turn the reference stuff purple. That rarely happens with home brewing. It's usually, you have to kind of really be high on the amount of catalyst for that to happen. And then there are various things that can happen depending on what is wrong with your biodiesel besides just the manufacturing process. So I haven't really talked about what happens when you store biodiesel and age it. There are various kinds of acids that can form over time. One of the issues with copper and brass and so forth that we mentioned, there's some issues with copper in your reactor, and one of those is that it essentially makes your fuel more likely to break down quicker. And luckily in home brewing, nobody stores fuel for any period of time. You guys are not going to be making enough of it to have it sit around long enough to get old and age it, because you're going to be putting it in your tank, unless you like have a sample like this that's several years old that you can carry around to show off. But most of the time, you're not generally running fuel that's 2 years old. In commercial biodiesel, they have to be concerned about that, because someone will buy it, put it in their farm tank, use it until it's half full, and then stop using it over the winter, and then start using it again the following year. And there's a concern that if there's that's a lot of time for the fuel to come in contact with oxygen, that begins a breakdown process. And if you had copper present somewhere during the processing process or storage process, the copper and some other metals can actually help they accelerate the breakdown that happens when the fuel comes into contact with a lot of air. It's not really that much of a concern in a home brew setting. I don't know. I can't think of many situations where that's ever where I think that would even really be a risk, just because people are usually using it pretty fresh.
The copper tubing as a bubbler in the wash tank?
Copper tube, well, I don't know what happens there. I mean, the copper tubing in a bubbler is like in contact with the water, but I'm sure there's copper coming into. I just avoid this stuff as much as possible. A lot of the time in homebrew situations, we've got basically we have a kind of a compromise going on between costs and basically the drawbacks of certain practices. So, for instance, there are lots of things that would be better to do than the way that we make them, than the way that we build our reactors, for example. But it's a cost issue. We work with, simple hardware store parts just because they're cheaper than brand new stainless steel from an industrial supplier. Same thing with the copper issue. We really tend to fudge things as homebrewers on the copper issue. Tends to be the brass that's in valves, because you really can't find stainless steel valves for very cheap. There's just a huge price difference, and so that tends to be where we wind up with some problems. So there's so this is so I just I'm doing the flip, just kind of doing a sample of the flip test. This is fuel that Bob grabbed from his desk at Rocky Mountain Biodiesel, and he thinks that it's probably good stuff, because he thinks that this is their finished wash fuel. So I want to sit that down. Don't over mix it. Like she said, it's supposed to mix it back and forth about 10 times.
Randall says 3.
Oh, really? His new directions say 10.
His instructions say 10.
Yeah. But anyway, so we're going to wait for this to kind of separate. We actually don't know much about what this fuel is. This stuff is probably several years old. It's also most likely under-converted. Can someone open this for me? My hand is damaged. And it's washed. Thank you. So these should be. We think that this should be washed fuel. So pretty sure about that. I'm going to do this. Hopefully we'll see it fail. This might take a few minutes before it actually happens, so we might be done with the class by the presentation by then. But any questions?
How sensitive do you think the pH test part of this test is?
I had some aged fuel that failed this test, and it was like
Failed it by being acid, but
by
not
being
by
acidic. Yeah, on the base side, does not seem to be very sensitive, because it takes a lot for you to get enough, for there to be enough catalyst in the. There has to be a lot of catalyst in order to turn the catalyst indicator purple, which basically means the red part of the indicator solution turns purple. Like
so a tiny bit of residual soap is not enough to change it.
Yeah, exactly. And it also doesn't seem like that the commercial tests for soap, the tests that have to do with testing for soap that are part of the ASTM biodiesel. Wow. So this is really bad. This is several years old, so it does make sense that it's aged. That's just going to happen. There's also hemp oil, which I believe falls in the category of oils that are not going to keep very well. But and this was made by Todd Swearingen, which means that we know Creighton's not laughing anywhere near loud enough. We need this guy.
That'd be nice.
But anyway, so yeah, so here we have aged fuel. Ignore the fact that it's green; it's supposed to be. But this was obviously like fresher stuff. So we're still waiting for for this to finish settling. But it was really obvious that there's acids in it. And most likely, if we did a titration on this, we would probably find that it's somewhat acidic. Okay. In fact, there you go. I don't know how much you're going to see with a black background, but so this is actually a pretty exciting innovation, because basically, if you got a load of fuel from someone that's been storing it and it does this, you got a pretty good idea. From a distributor's perspective, you got a pretty good idea that that's going to have most likely has acids in it, and acids and metals in a fuel system really don't mix. That's where you're going to get hitting and corrosion pretty quickly. So that's a really good. Now that is something you could test yourself with a titration. I don't actually know how this works. This is a proprietary process, so we don't know what exactly it's doing in order to test for what they call aged or oxidized fuel. Most likely it's just water-soluble acids, but we don't really know that. So the next thing would be to go to the lab right now and actually see why this failed, because if this is slightly acidic, that would probably be one of the answers. But there might be some other property that they're testing. It probably there's probably other alternatives to that. Also, there's a bunch of debris. Oh, looky, there's a bunch of stuff floating on the interface. So this is we can do a whole photo session with this later. This is priceless. Yeah.
Do you throw that fuel away? Is there some way to reheat it?
I think they actually recommended re-reacting with, or hitting it with magnesol, because it absorbs some of the byproducts of aging. Maybe we should talk about aging and breakdown a little bit more, even if you're not going to run into that in homebrewing. So biodiesel is biodegradable, which is really great, except when it comes to when you want to store it. So it biodegrades for several reasons. One of them is that bacteria attack it. you've got water present, water attacks it, it'll hydrolyze, it'll like break it back up basically. But it also, it also produces really nice conditions for bacteria. So whatever you do, don't store it in a tank that might have had some water in it if you're going to keep it for a long time. And that's actually more difficult than it sounds on a large scale. Like on a large scale, there's often water present in fuel tanks, partially because they breathe. They'll expand, the air will expand and contract from night to day, and humid air will get in and then condense on the metal walls and drop down. So that's one of the concerns about having something like a large fuel tank that's several hundred gallons on somebody's farm that's half full for a season. Biodiesel is just more sensitive to water in the stored, in storage, and that's one of the issues is that it begins to attract or begins to feed bacteria better. When bacteria start attacking biodiesel, they produce acetic acid and formic acid, I believe. Somewhere in the breakdown process, whether it's the bacteria that do it or if it's just a natural byproduct of breakdown, there are a few water-soluble acids that are formed. And water-soluble acids in metals is just death for fuel systems. Peter.
Just in storage, if you ran a nitrogen blanket on top of it, would it slow down the
Yeah,
process?
nitrogen would help a whole lot. Keeping oxygen out would help, but it's rare that people really go to those lengths. Usually just normally these are problems that affect diesel fuel too. You usually don't want to store it in a half-full tank with water in the bottom. So in that kind of situation, what they usually suggest is like if you're going to store a tank full of fuel for a long time, fill it all the way. Get it totally full. Don't store it half full so there's not as much oxygen. Are we at the end?
Oh.
No, never mind. You were standing there as if you were here to kick me off. Okay, never mind. Anyway, so that's kind of that's an issue, just storage and the breakdown products when this breakdown process begins is that it oxidizes, it forms water-soluble acids, it forms free fatty acids. The titration that you learn how to do when you make waste vegetable oil biodiesel will tell you about both of those. It doesn't matter which one you have. If you have acids, you've got a problem. They don't belong in your finished fuel, and that's usually the first thing you want to. That's the easiest indicator. So obviously there's that's going on here. This is because this is also another indicator for acids most likely. And the other and then there are various kinds of precipitates that can happen as this fuel breaks down long enough. So if you have all sorts of you might get layers of stuff that probably isn't going to spray right, and so but that's kind of just don't bother. Don't use fuel that you have found has acids in it, and acids is kind of one of the easier tests to do. It's just the ordinary titration. If you're producing your own fuel, it's just the ordinary titration.
In one of the other sessions, critters growing in the biodiesel was mentioned. Is that something we would have to worry about as home brewers, or is that more commercial?
It's if you put any fuel into a tank that already has bacteria in it, like a bacteria culture in it, that might set off. If it's biodiesel or vegetable oil or something, it will set off. They will eat it more rapidly, so you'll get more of a growth in bacteria colonies, and that can start that process. But it doesn't necessarily just show up all that. It doesn't show up all that easily. I mean, if you have a big open vat of fuel sitting around open to the air, you're going to have, which can happen in a processing situation. You could get bacteria in it, but it's kind of rare. And biocides that are made for diesel fuel will take care of it, like that. Biocides and a lot of fuel filter changing and sometimes purging of whatever's in your tank. So, but go ahead.
Is that a problem I can run into when introducing biodiesel in your tank for the first time? It's been running petro for all time.
I think it's exaggerated. I'm sure it can happen, but it's not that common.
Is using biocides in storage a standard practice?
I don't think there is standard practice for homebrewing. I don't know whether commercial biodiesel producer would do it. I don't think so.
And it depends on the estimated residence as well.
Yeah, if you're gonna store it over the winter because you're someplace, it's 40 below where you live, and you're gonna not use it for a while, and you think that it'll actually defrost long enough to grow something, then sure put biocide in it. What else? They're a truck stop kind of. They're sort of at there tends to be something that's sold at some auto parts places and a lot of truck stops. Marine supply places will sell it. Yeah, I think you can get it by mail. I'm pretty sure. But it's
store oil or biodiesel?
Oil will actually break down pretty rapidly in storage if there's bacteria in it, and that's often the case when you're collecting oil from restaurants. There's often when you look at a restaurant grease bin and it stinks really bad. That's sort of the beginning of that breakdown process, and you probably could stop that by dewatering it and then keeping it sealed. But that's actually like half the work. You know, by the time you dewater it, you might as well let it cool down and make biodiesel out of it. But in terms of storage stability, in terms of testing stored fuel, the testing that's available to you is really the titration that you learn for working with waste vegetable oil, or it's a flip test if you're something like a distributor and you don't actually have you're not messing around with chemical reactions. So basically anything that goes wrong with biodiesel in storage starts out as a rise in acidity. So like typical. Like on the homebrew titration that we do, the typical of homebrewing is about a 0.2 on the titration maximum. You know, I think that there's actually a standard for it in ASTM that I don't remember, but it's in the ASTM standards. But for the homebrew, the particular type of titration that we do when we make biodiesel, if you do that to a sample of washed fuel that has been fully washed, then it'll be somewhere around 0.2 or less. And if you start seeing that rise much above that, then, you know, especially if you test it like when you put the stuff into storage at the beginning of the winter and then test it again later, if it's gone up, that may be an indication that like breakdown is occurring. Another major issue is just how much oxygen contact causes breakdown to start happening. There are a lot of things that home brewers do that do lead to increased contact with oxygen versus what a commercial producer is supposed to do. And one of them is bubble washing, one of them is bubble drying, and then basically all of the drying methods that we use pretty much rely on air contact with the fuel in order to get water to leave as water vapor. And there's a lot of concern, mostly from the people who made this. There's a lot of concern about how oxidation, how that introduces all these oxidation problems that will cause your fuel to go bad and break your car. Realistically, people who bubble wash and aggressively bubble dry still pass all of the tests that exist for that are lab tests. So it's really, you have to do it for a lot longer than normal. Normally you bubble dry for about 6 hours, or you circulate with the fuel splashing around through the air. If you want to promote oxidation in an oil commercially or in a lab setting, I think they do it for several days with UV light present, and it's like a much more intensive, sort of more aggressive contact with oxygen. And commercially, in terms of how they dry, they're often going to do it under vacuum or in some way where there's heat really accelerates the driving off of that water, so they have less air. They don't need that air contact as much as we do during the drying process.
How's their flip testing?
Okay, so we have, well, I'm not really sure exactly what happens when the flip test shows more than one thing wrong. These guys are experts. So do you want to talk about the flip test again? Because you guys have the most real experience with it.
My problem with the flip test is Randall. See, Randall buys fuel at our station, you see, who invented the flip test. And Randall, there's like different standards for Randall. There's the Randall, I run this fuel in my boat test, which needs a .0001 on the GC for total glycerin. Right? So he comes in and goes, oh, I'm going to buy your fuel today because it's really, really good. And then he'll be like, oh, I'm not buying your fuel. Do you still have that stuff? Because I'm not going to buy that. And it's like, it's ASTM quality, but it doesn't pass the Rando boat test. So, I mean, we're kind of, I don't know, but Gretchen.
We need to have, I've not seen it very often do this separation of red on the top.
Oh, that might be isn't that a light thing? Because see how it's doing that. See how it looks like it's separating on the top right there. Let's look at his reference. No, his reference tester is doing the same thing. Okay. This is his reference.
Yeah, I think it's the reflection.
Yeah, because I'm seeing red right on the top too, but it's not. It's just the lights.
Well, he says that a little bit of cloudiness like this also means some glycerides, but we've had some of the stuff that did that tested, and it actually tested fine with glycerides, so I think there may be some more factors at work.
Yeah, so traces of hygroscopic glycerides and oxidized esters, which is basically two different, very, very different things, make the fuel cloudy. So that's hard to.
And I actually need to talk to him maybe temperature or humidity or some other things could be making
You weren't holding your tongue out when you shook it.
We do have,
So he also likes to see a really clear line, like a clear
Yeah.
finish between the two
which we're not seeing there.
fluids, which we're not seeing here.
Are you
But
seeing
we don't actually know what this is either. Like this was just a random
Yeah.
sample, because this might be
This looks
opposite.
pretty typical of commercial field
Mhm.
to me.
Is there a little like crud in the interface there, or is it completely?
No, it's not crud.
I
It's
mean,
not
is there
crud.
something there? Or?
I thought I saw something. I see little. I thought I've seen some little bubbling there. See that? Right there? Or is that a
That
reflection?
it needs to settle out a little bit.
Uh-huh.
What you will see sometimes is just like your regular water wash test, you'll see sometimes like a layer of soap scum or something at the bottom otherwise, and that would be another thing you would want to avoid. But to me,
Supposed to
from all
be clear.
comparisons I've done, this looks pretty good.
Mhm.
It's not quite as perfect as the Randall standard.
Well, this has also been settling for days too, so that's actually
It's
very
pretty good. This, on the other hand, clearly fails onto.
Sometimes it gets cloudier after it settles rather than clear. I've had it be clear right away, and then the next day be cloudy.
I've seen that too, and I'm not sure why.
So I don't know how to interpret the test very well.
Yeah.
I think the test is fine, I just can't interpret it.
Yeah. Well, one of the reasons it's giving out samples is so that people, so as to get feedback like that, like I can't interpret this, and he doesn't sell it as a real super exact, as necessarily being a super exact sort of a indication of quality. It's just meant to be.
I think it's great for testing for what you're testing for, which is the fuel aged, and I think that's what he designed it for originally.
It's also useful. It's useful for us, like when we get a delivery, we've only got 200 gallons of fuel left, and we're going to be out of fuel that day if we don't take the delivery. It's not like we have time to go take it to a lab and have it tested before we take it. So it'll tell us if there's something really wrong with the fuel. I have seen them turn purple.
So that if we call you and ask you, did you just accept the load really quickly? And okay.
No, we would use this. This is something we can test for on the spot before we let them fill up our tanks. So it's useful. Everything that's failed this blatantly failed it doesn't pass the other ASTM test.
Yeah, you have had some stuff fail that but pass ASTM, is that right?
Only the very subjective things like, whether or not this is considered cloudy. I think
Well,
it's clear
the
enough.
other thing is that cloudiness is also, on this test, is also a measure of like how well they washed it, if it's got a lot of some soap in it, I think. And so, I think,